Good morning, my name is Nicolas Prantzos. I'm working in the Institute of Astrophysics in Paris, mostly on stellar evolution, nucleosynthesis, galactic evolution. But today I'm going to present you a few topics which are essentially at the periphery of our quest for life in the universe. They are not main topics, there is nobody working preferably on those topics, but when you read the literature about research for extraterrestrial life, you will often come across those subjects. We thought with Miriel it would be interesting to introduce those things in a course, in lectures on research for extraterrestrial life and astrobiology. What I'm going to present is based on a couple of papers that I have published a few years ago, both on the so-called galactic habitable zone, which is a rather recent topic. It appeared in the early 2000s, and the Drake equation and the Fermi paradox, which are much older topics. They are here for at least 50 years or 60 years. So let me start with the concept of the galactic habitable zone, which, as I said, emerged by analogy with the older concept of the circumstellar habitable zone, which was first formulated by Huang in 1959. And the idea of the circumstellar habitable zone is the region around the star where the conditions of temperature allow for the presence of liquid water, because we think that liquid water is very important for life. So depending on the distance from the star, it may be too hot or too cold for having liquid water. And in the case of our solar system, where you see there, the Earth is right in the middle of the so-called habitable zone of the Sun, where other planets, for instance Venus, is just inside, Mars is just outside, and the giant planets are much further out. And of course this habitable zone, the smaller the star, the less luminous it is, the closer it is to the star. So all this is known for a long time, and a large part of current research is to find planets around other stars which are not at any distance, but especially in what we call the circumstellar habitable zone. Here is a more recent diagram from the Kepler telescope, where you see something which is equivalent to distance from the star, but it is essentially the distance where it's the effective stellar flux, how much flux you receive from the star, because the flux decreases with the square of the distance. So this factor is included here, and you see again one effective stellar flux is the flux received by the Earth from the Sun, which is a star of 5,800 Celsius temperature, and the planets that have been discovered by the Kepler telescope are within, some of them are within this habitable zone. So now we start discovering planets within the habitable zones of their stars. And these are the planets we are mostly interested in, of course. Okay, but now let's come to the galaxy. The galaxy has properties which vary with radius. We shall speak of those properties in a moment, but they have properties which depend on radius, and they vary also with time. And the question is, are some of those properties important for the appearance of life in the Milky Way? For the appearance, for instance, of telluric planets, or for the destruction of life? Because we could also think about, for instance, supernova explosions that are threatening life. And this is how the concept of what we called first belt of life in the galaxy emerged in the 80s, and it took the more modern name of galactic habitable zone in 2000, after this paper in Icarus and Scientific American, and especially that paper of Lineweaver et al. In Science in 2004. A few things about the Milky Way. So it has about 100 billion stars, and the radius about 50,000 light years. This is a picture, a true picture of the Milky Way in the infrared. We see it from the edge. We are inside the Milky Way, so we see it from the edge. And its age is estimated to 12 billion years. And about half of the stars have been formed before the Sun. They are older than the Sun. It has a disk, a bulge, and there is also a lot of dust and gas, mostly concentrated in the plane of the Milky Way. About 15% of the total mass is in the form of dust and gas. If we could, and the Sun is at the periphery about 26,000 light years from the center. If we could have a look on our galaxy from above, this is again a design, we could be a spiral galaxy with a bar here. And the Sun would be somewhere around here. We have a quantitative picture of the various properties of the Milky Way as a function of radius, distance from the center, expressed here in kiloparsec. A parsec is 3.26 light years. The Sun is at 8 kiloparsec from the center. You see the profiles of gas. It is more or less flat with less gas in the inner galaxy, but for the most of the disk is flat. These are surface densities. You condense everything on a surface, so there are about 10 solar masses per parsec square of gas in the solar neighborhood. There are about 40 solar masses per parsec square of stars. The stellar profile is exponential with a scale length of about 3 kiloparsec. And this is the profile. We know that there are many more stars formed in the inner galaxy than in the outer galaxy. There are more supernovae in the inner galaxy also, because the massive stars explode in the end of their lives as supernova. We shall see in a moment. And this is also exponential with a scale length of 6 kiloparsec. And there is also a profile concerning the abundance of the metals. They are not evenly distributed everywhere. There are more metals per unit mass in the inner galaxy than in the outer galaxy. And by the term metals in astronomy, we mean everything which is heavier than the two light elements, hydrogen and helium, that were formed in the Big Bang, as we heard from Mark before. So here's the profile of metallicity, which is also decreasing outwards. So again, some facts about the Milky Way. And we can ask, this is the present picture, how all these properties evolved with time. What was the picture of the galaxy? We go backwards in time, what we would have seen. We don't really know that. We have still some problems in reconstructing the history of the Milky Way. We have models, for sure, but we do not know how representative of reality these models are. Here I will show simulation. There are many such simulations you may find. These simulations take thousands of hours in some of the most powerful computers. Remember, Mark said that the universe was quite uniform. And the question is how, from this uniformity, the complexity we see around us emerged at small scales. So you see small overdensities of matter collapsing under their own gravitation, coming together. These are gaseous. What you see there is essentially gas. And you see how rotation is enhanced as time goes on. These are the earliest moments in the life of a galaxy. It's far yet from being a spiral, but you see that lit by lit, you're forming a spiral galaxy. And at some point, there will be less activity, less merging there. But again, this is just a simulation. Does not mean that this is how things happened. We hope it is close to reality, but we don't know yet. But the nice thing is it's a high-resolution simulation. You see things in exquisite detail. You see the bar forming now in the inner galaxy. A small bar, but it will increase as time goes on. And more material is coming progressively from outside. And at some point, presumably, the Sun appears also after 4 billion years. Unfortunately, the time does not appear there. It's unhappy, but we have no idea of the time scale there. But you see now that the galaxy is more or less formed. There is very little material coming from outside now, and it evolves more or less independently of its environment. So the environment plays a particularly important role, especially in the early times of the galaxy formation. Okay, this could go on for some more time, but we can move on. These simulations do not include everything. They have very little chemistry, for instance, because what happens, this is during this dynamical formation of the galaxy, is that the gas also turns into stars, and stars produce metals, heavy elements. We know now that it is not in the Big Bang that the metals were formed, metals that are important for life, but they were formed much later through the action of stars, the nuclear reactions that occur in the hot interiors of stars. And there is a kind of cycle of matter which goes from the material coming from the Big Bang, hydrogen, helium, and some other light isotopes. You form galaxies, and in the galaxies you form stars, small stars that live for billions of years, massive stars that live for a few millions of years. That's short-lived. And especially in the advanced phases of their evolution, because in the early phases they just bring hydrogen to helium, but in the advanced phases they burn helium, nuclear burn helium, to heavier elements. Small stars end up as planetary nebulae, and they eject their envelope, including some carbon and nitrogen, but it is mostly the massive stars that explode as supernova, and they eject whatever they have cooked in their interiors in the interstellar medium. In the end, they leave behind either white dwarfs or neutron stars and black holes for the massive stars. And in the case you have binary stars, and about half of the stars in the galaxy are in binaries, when they are very close binaries, the white dwarf can accrete material from its companion, go beyond what we call the Chandrasekhar limit, and explode as another type of supernova, called thermonuclear supernova. These ones are called gravitational supernova. They explode after the collapse of their iron core, and then they produce most of the iron, the thermonuclear supernova. All this material is injected in the interstellar medium, where spallation by cosmic rays create the light elements lithium, beryllium, and boron. This is a very special case. And then again, from this material, new generations of stars, more enriched in metals, are formed. So this is the cycle of matter that we can describe by the so-called models of chemical evolution, galactic chemical evolution, where the properties of stars play a very important role. Here you see some of those properties, a function of the initial mass of the star in solar masses. This is the mass of the sun, 1 in this scale. These are the massive stars up here. You see the distribution by number of the stars. There are very few massive stars, in fact. Most of the stars are low masses, even less massive than the sun. 0.1 solar mass stars. This is, for instance, the closer star to our solar system, Proxima Centauri, is a star which has 1/10 the mass of the sun. And this is the lifetime of the stars expressed in millions of years. So you see the big stars, the massive stars, live a few millions of years here. The sun lives 10 billion years, and the more massive stars, the less massive stars, like Proxima Centauri, live about 1,000 times more. And of course they do it because they burn very parsimoniously their nuclear fuel. So the massive stars that are short-lived produce most of the metals. The less massive stars produce a few metals. And by the word metals, again, this is the definition. And there is also the term metallicity, which is the fraction of the metals. In the sun, for instance, it's 1.5%. Okay, only a small fraction of the mass in the universe, of the material of the universe, is in the form of elements heavier than hydrogen and helium. Hydrogen and helium really dominate. They come directly from the Big Bang. So you know, for instance, that of course the calcium, the iron, in our body are coming from the stars. They have been cooked in the stars at some point in their evolution. But in your body you have also water. 70% of the water, of the mass of your body is in the form of water. So if you weigh, I don't know, 70 kilos, you have about 50 kilos of water in your body. And in the water there is hydrogen and oxygen, 1/9 of the molecule of water is in the form of hydrogen. So 1/9 of 70 kilos means around 5 to 6 kilos in your body is in form of hydrogen, and this comes directly from the Big Bang. Okay, because there are no process in stars to produce hydrogen. Stars are destroying hydrogen. So a part of your pod is directly coming from what Mark described a couple of hours ago. So now we have models to describe this chemical evolution of the galaxy. We follow all this cycle of formation of stars according to their mass, how and when they die, how much material they eject in the stellar medium in the form of such or such metal. And we compare the results of the models to the composition of the solar system that has been known for a long time. And what you see there is a comparison between model and observations. Observed are the black curve, and there are two curves there. There is a black and a red one. And you see that there is a very nice superposition of them. This means, and this is one of the triumphs of the astrophysics of the 20th century, the fact that through what we call now nuclear astrophysics, we managed to understand how the composition of the sun and in general, but for other places in the universe, we do not know their composition to this exquisite detail. It resembles, it's close to the sun, but we have not such precise observations. But at least we managed to understand the observation, at least for elements up to zinc here. For the heavier elements, it's a little bit more complicated. But you see how well we understand now the various nucleosynthesis processes, because there are many of them that lead to the composition of our solar system. And this is why Willy Fowler, who was a nuclear physicist in the United States, got the Nobel Prize in Physics in '83, because the production of these elements depends a lot on the nuclear reaction rates that take place inside the stars. And in his laboratory, he measured a lot of those nuclear reaction rates and evaluated others. But there was a kind of a scandal there, because the guy who had the theoretical ideas beyond that, who thought that elements are made in stars, was Fred Hoyle, a British astronomer. But he had also other very radical ideas about the origin of life, and he was not in good terms with a lot of his colleagues, so he did not get the Nobel Prize, and this was a small scandal. There are many such scandals around the Nobel Prize. But he is the only astronomer, modern astronomer, that I know that he has a statue for him. He is in the Cambridge Observatory, because he founded the Institute of Theoretical Astrophysics in Cambridge in the 60s. Okay, so we apply this kind of chemical evolution models to more simple models of the evolution of the galaxy, not the numerical, very detailed model I have shown you. These are very simple models for the dynamical evolution of the galaxy, which essentially consider the galaxy as an ensemble of concentric disks, and each disk evolves independently, but in a different rate. And you see the profiles of various quantities. These are the color lines, curves, for different times. 1.5 gigayear is the green line, 5 gigayear after the beginning, the purple line, 13 gigayear, the final thing, the blue curve, and the final thing should be compared to the observations which have just seen, the yellow shaded areas there. So it's more or less a nice description of the galaxy, at least the present day galaxy. What happened in the past, we don't know what the profiles were in the past, several billions years ago. We hope that our models represent correctly that, but we cannot really check it directly. But we know that the galaxy was most probably formed inside out. Most in the earliest phases, we have seen the dynamical simulation, the inner galaxy, and later the outer galaxy. So now comes the big, the connection to our story, the galactic habitable zone. Which of those factors may affect the formation and the destruction of habitable planets, or of life in habitable planets? One of the things that were understood in the early 2000, when we first started having statistics about the extrasolar planets, was that, okay, in the beginning we have seen mostly very massive planets, Jupiter-like planets, and very close to their stars. Why? Because it was easier, taking into account the techniques that were used in these days, How could we see the stars? We cannot see, planets, not directly, because they are much less luminous than their star. They are billions of times, the stars are billions of times brighter than a planet. So we use observations of the trajectory, the orbit of the star. And if there is a planet around the star doesn't move straight straight line in the sky, but it wobbles around its the position of the center of mass, because there is a planet around. And the bigger the planet, the closer to the star, the bigger are the perturbations in the trajectory. And this is something we can detect through Doppler shift. And this is why in the beginning we have seen mostly Jupiters. It took more years to detect small planets around the star. There are some other techniques now, but this is how it happened in the beginning. And when we did that, we realized that the number, a fraction of stars that had Jupiters around depended on the metallicity. This is the metallicity, the amount of iron, for instance, of a star, in a logarithmic scale, and divided by the corresponding solar metallicity. Okay, which means that 0 here in this scale is the metallicity of the Sun. Minus 0.5, it's a logarithmic scale, is 1/3 of the metallicity of the Sun. 0.5 is 3 times the metallicity of the Sun. So you see that around stars that are more metallic than the Sun, it was easier to find. We had observations showed that there were more Jupiters. And there is an analytical formula going through that. This is metallicity square with respect to the Sun. But and in the beginning this was a surprise. Why so many Jupiters? I mean, in the solar system, the Jupiter is far away from the Sun. And it's a gaseous planet. How can you expect to have gases gases so close to the Sun, which pushes them, radiation pressure pushes gas outside? And then we realized, I mean, the theories we have now for the formation of Jupiter so close to the Sun is that their suns, their stars, is that they were formed far away. And then they migrated by interaction with their protostellar disk. They migrated and they lost angular momentum, and they came close to their star, and that's how we observed them. But during this migration, they should have destroyed any other planets on their way. They didn't have allowed to form any other planets. So detecting Jupiters close to their stars means that there are no terrestrial planets, because after all, for life, at least as we understand it, we need terrestrial planets. What about terrestrial planets? Now, after a few more years of observations, we think that this condition of metallicity is not valid for terrestrial planets. Here you have, as a function of the planets that have been observed around other stars. And as a function of the radius of the planet, here are small planets like the Earth, here are Jupiter-sized planets. You see that the metallicity of the parent star, for the small planets we find them everywhere, at all metallicities. This is solar metallicity, this is 3 times solar, this is 1/3 solar. So we have terrestrial planets everywhere. It's only the very big planets that are found at high metallicities, what we have seen before. Okay, so for Jupiters, it seems this diagram, which is an observational diagram, it tells us that for heavy planets we have to go to very metallic stars. And metallicity increases with time, so it's late in the universe, in the evolution of the galaxy. For small planets, they can appear quite early, even at small metallicity. This is a nice thing that we learned from the observations. So now we can try to play a little bit with those things. The probability of having Earths not destroyed, because if you have hot Jupiters at high metallicity, then you may not have Earths. They are destroyed. So the probability of having Earths is the probability of forming Earths times 1 minus the probability of having hot Jupiters somewhere. And here are the results of 2 works. One, the red is of mine, later in 2008. The earliest one by Lineweaver in 2002. You see how he accounted for the probability of forming Earths and hot Jupiters. And yeah, the bottom line is that in his case, the probability of having habitable Earths is favored at high metallicity. And in my case, it's more or less independent of metallicity. It's closer to the modern picture anyway. But they were the first to make this kind of calculation. Then, once you clarify more or less what are the conditions for forming Earth, which is quite speculative at this time. It's based on observations, but we don't have a real theory behind it. Then you can ask, what are the threats for life, at least for life as we know it? And the most commonly advocated is supernova, either gravitational or thermonuclear supernova. There is also something you may see sometimes, gamma ray bursts. This is more or less something to scare people, because gamma ray bursts are very rare events. They are occurring very rarely in the galaxy, and probably not in the present day galaxy. We observe them in regions of low metallicity. Our galaxy today has a high metallicity for the last 5 or 6 billion years. So these things are certainly not happening in our galaxy for a long time now, at least since the sun's formation and even before. So what happens when you have a supernova is that there is a tremendous amount of energy released, 10 to the 47 ergs in UV, life a few hours, 10 to the 48 ergs in X and gamma rays for a few months, and 10 to the 50 ergs in cosmic rays these are high energy particles accelerated by the explosion for a few thousands of years. And what is the impact of those particles? It depends on the distance of the supernova, but what they do mostly is they are ionizing the atmosphere. The impact of ionizing radiation in the planetary atmosphere is that it induces chemical reactions which produce oxides, nitrogen oxides. And these nitrogen oxides interact with the ozone layer of the atmosphere and they destroy it. They create, all these, the concern we have now about the hole of ozone above the Antarctic. And in that case, there would be, because of atmospheric circulation, no ozone layer, protective ozone layer, letting the UV radiation of the sun come inside and destroying all life forms on Earth. This is the basic impact of supernova. When you hear about the threat of supernova explosions, you might think that we are directly affected. Life could be directly affected by that. But this is not the case. The threat is not the direct impact of supernova on life on the Earth. For that, you would need a very, very close by supernova, which is quite improbable to occur. The basic impact is through the destruction of the ozone layer by ionizing radiation. And, but even that is not sure, because in some cases, mutations may accelerate and even induce evolution. And also, this threat through the destruction of the ozone layer concerns the land life. Marine life below a few meters of water is basically immune to this danger. So this does not mean, even if we have a close-by supernova, even if life is completely disappears on land, does not mean that all life on Earth will disappear. So now, since we know a few things about the frequency of supernova explosions, how many we have in the galaxy, and we can calculate their occurrence in the solar neighborhood, for instance. You see here that the occurrence time is about 2 gigayears in the solar neighborhood. It is shorter in the inner galaxy. There are more supernovae in the inner galaxy. And again, they concern land life. And even if you destroy life on land, after that life on land appeared before about 400 million years, even less. So it means that in 100 or 200 million of years, again, from the marine life, you can have life on Earth, and then evolution to intelligence. So this is not definite sterilization of the planet, because we know that there have been several extinctions in the past of the history of the Earth, but the planet was not sterilized. Life not only survived, but it evolved to higher levels of complexity. Anyway, what do you do if you want to describe the threat of supernova for life and to quantify it? In my sense, it is impossible to do it. But that's what these guys did. Lineweaver in 2004, they took as a unit in order to describe the threat of life on Earth how many supernovae appeared in the past 4 billion years in the solar neighborhood. And this is the unit. This is the symbol for the sun. And they quite arbitrarily declared that if this unit is higher than 4, this is 4 here, in these units, then the probability of life surviving is 0. It's here. If it is less than 1, the probability is 1, because we are here, after all, with all this activity of supernova in the solar neighborhood. And there is some curve between the two. That's worth for whatever it is worth. Okay, probability is 1 if the supernova is less than, and 0 if it is more than 4 units in these units here. And then if you have a model of galactic evolution, you can go, the one that I have seen before, you can apply this and look how the various factors evolve with time. Again, as a function of the radius from the galactic center, probability of forming Earths after 1 billion years, 2 billion, 4 billion, 8 billion years, 13 today. Today you can form, there are a lot of metals everywhere, you can form Earths. The probability of forming hot Jupiters is much more depending on metallicity, okay? Where for Earth-like planets it's more or less independent of metallicity, but for Jupiters it is dependent on metallicity. Then Jupiters somehow affect the formation of Earth-like planets, but not so much. This is for surviving the hot Jupiters again. And this is the time-integrated supernova rate at various moments. The probability of surviving supernova, it's smaller in the inner galaxy, but not so small. This is a logarithmic scale. Okay, but in the outer galaxy is unity. There are not enough supernova. And so the final result is the probability of having Earth surviving hot Jupiters and supernova explosions. Okay, it's a little bit less in the inner galaxy than in the outer galaxy. But it's not a big deal again. Remember, there are many more stars in the inner galaxy. So if you put this in this kind of diagram with radius and time here, we start from here, we are today here, the probability of having Earth around one star, it's bigger when you are in this region. And this is what is called a galactic habitable zone. But again, you may think if this has any meaning at all, because remember there are many more stars in the inner galaxy. So if you multiply this probability by the density of stars, which is higher in the inner galaxy, you get this thing. Now you find more Earths in the inner galaxy than just in the habitable zone there. So these are two different things. This is the probability of having life around one star at a given position, and this is the probability of having life hosting planets per unit volume or surface density in a given position. So if you look at this diagram, the term galactic habitable zone doesn't have so much meaning. This is the difference between what Lineweaver found, and these are my calculations. But they made a lot of publicity out of this. There was a paper in Science. Since then, other people played the same game, and you see here the results of this table, a summary made by a guy last year, where you see various calculations. You see some people find, I believe the entire disk is okay for Earth, for life hosting planets. Some people find that they are predominantly in the outskirts. It has certainly to be a result of the assumptions they made for the supernova threat and so on. So to make, there are other more evolution, there is evolution in this topic, because now we think that stars, once they form at some distance from the galactic center, they come closer and then they go further out from the galactic center, not only because of epicyclic motions, they follow kind of epicycles, but also because they can really migrate their interactions, dynamical interactions with the spiral arms that can kick stars outwards or inwards. And there is a lot of migration taking place in the disk of the Milky Way. We know that for the last 15 years or so, and there are models. And this makes even more complicated the game of evaluating, since a star can migrate outwards. In fact, we believe that the Sun was not formed at 8 kiloparsecs from the galactic center, but it was formed at 6 or 6.5 kiloparsecs. There There are several indications that push us towards that idea. So since stars can migrate everywhere, it becomes more complicated to evolve all these things. This is a more new calculation, but I will skip it. So this is a summary of the first part of my talk about the galactic habitable zone. It is impossible to define either qualitatively as a probability of creating versus destroying habitability by various factors in the Milky Way disk, and even quantitatively. The more so because radial migration of stars mixes stellar populations across the Milky Way disk. So does this mean, on top of that, there is simple and sea life forms appear to be quite robust, and that means quasi-immune to cosmic catastrophes. Does it mean that it is a useless concept because it has no explanatory or predictive power? I'm not sure. I think that it may help us to structure our thoughts or educated guesses or knowledge, whatever we know or we think we know, about a very complex phenomenon, which is the emergence and the survival of complex life forms in a galactic environment. Remember, the concept of circumstellar habitable zone I mentioned in the beginning, it's only about the emergence of life, conditions favoring the emergence of life. The concept of galactic habitable zone introduced also one more thing, the conditions of destroying life, not only of emergence, but destroying life. And it's the game between the two that may lead to a belt of life in the galaxy, although, as we have seen, it's very hard to predict it. But again, it may be a useful concept, the same way as the concept, and this will be the next topic, of the Drake equation. I don't know how many of you have heard about the Drake. Okay, one last thing before getting there. The guy who coined the name galactic habitable zone in 2001 was somebody named Guillermo Gonzalez. He was working in the States. He was the first to notice the correlation between the occurrence of Jupiters and metallicity. And then he started playing all that game and pushing those ideas. And then we discovered that he was somebody who had some religious conceptions. And this is an interview he has given to some Christian journal in the United States, newspaper, where he proposes that his point was to show that the Earth had some special place in the galaxy. You know, since the time of Copernicus, we dropped the idea that our planet, even our solar system, has something special. But in a sense, he wanted to bring back this concept, that at least in the case of the galaxy, the Earth and our solar system had a special place concerning metallicity, specific metallicity, being far away from the threat of supernova, and there was some kind of intelligent design. You know, perhaps that these ideas they have some support in the United States these days. But he said that such views are denounced as pre-Copernican, and that he is not leaving his philosophical preconceptions to color his interpretations. But in the end, he was kicked out of his university. He found another position in some college, and then, as far as I understand, he's not working in astronomy anymore. But he started those ideas. So let me go back to the Drake equation. It's a much older concept formulated by Frank Drake in 1961. And there is an institute now, the SETI Institute in the United States, and this is what is in the entrance of the SETI Institute, this famous Drake equation. It's all started back in '59 with a paper written by Giuseppe Cocconi and Philip Morrison in Nature on searching for interstellar communications. And they proposed that the best way to search for interstellar communications would be through radio waves. Why radio waves? Because they are less absorbed by the gas and the dust that exist in the plane of the Milky Way. You probably don't know that when we look in the Milky Way, we cannot see far away, just a few kiloparsecs from the sun, because radiation from further inside is absorbed by dust and gas. But not radio waves, they are not absorbed. They go through dust and gas. And also, the other advantage is the radio waves, they are at lower energies, so they consume less energy. You can transmit the same amount of information with less energy. So that's they suggested that we should look for radio waves, artificial signals, for interstellar civilizations. Now you see it's in another level, not just life, but intelligent life. And this is also something we should have in mind when we speak about life in the universe. It's, when scientists speak about life in the universe, most of the time they have in mind microbes. Because you know that for the largest duration of the Earth, the life forms were extremely simple, simple bacteria. Complex life came in the end, and intelligent life in the very end. So if we find life somewhere in the universe, in all probability it would be bacteria, not humans. But these, not complex, very complex life or intelligent. But these guys were interested in intelligent life, able to exchange artificial signals. And they rightly said that the probability of success is difficult to estimate, but if we never search, the chance of success is zero. This was the ending sentence, which became famous by then. Now, Frank Drake was a young radio astronomer then, and he was the first to take these things seriously and to start a project called OSMA, from the famous land of Oz in the Count, Count for Children, by monitoring two nearby stars, Tau Ceti and Epsilon Eridani, for a few months. Of course, he didn't detect anything, but in '61 he made a conference in Greenbank, in his radio telescope in Virginia, on radio communication with extraterrestrial intelligence. It was the very first conference on that topic, attended by only 10 people there, among whom the very young at that time astronomer Carl Sagan, the age of 27, and Philip Morrison also, and a couple of other guys. And preparing the agenda of that conference, Drake tried to evaluate the chances of detecting signals, radio signals, taking into account that our galaxy has a lot of stars, about 100 billion stars, and to see how many of them may have intelligent life or civilizations on planets orbiting them. And he formulated this famous equation, you see him there writing it in fact, where n is the number of civilizations in the galaxy, and it's a product of various factors, where the first one is the rate of star formation in the galaxy, how many stars are formed. Then you have the fraction of stars with planets, how many planets there are around the star, this is NE there, the fraction of habitable planets, not just any planets like the Earth, the fraction of planets where life effectively appeared, where intelligence appeared, where technological civilizations, and finally, this is a rate, so it's per year. So you have to cancel it by the lifetime in years, the lifetime of civilizations. And we shall show that this last factor plays a big role. Now, in the time when Drake formulated this equation, only the first term was known. We had some idea about the rate of star in the galaxy.
Nicolas, we assume that they're all independent.
And on top of that, we assume that these are the appropriate terms already. There are no other terms, and they are independent of each of them. But this is the state of the art. They are fractions, in fact. Many of them are fractions, not all of them, but a few of them are fractions. So when Drake formulated that, only the first term were known. We didn't know about any other extrasolar planets. Now we have some ideas for, and I shall show them in a moment, for the fraction of planets and the fraction of habitable planets, in fact. But we have no idea for the product of those fractions, where life effectively appeared, where intelligence appeared, communication, technological civilization appeared, or the lifetime of any of them. So we cannot say anything about the number n. The only way to do so is if we ever detect at least a second an extraterrestrial intelligence. Then we can start doing statistics. But then our quest will have arrived at an end without using this Drake equation. So the basic thing is that this Drake equation has not any predictive power. And depending on what kind of values we put there, you can find any result. It is significant in my sense that the early evaluations, if you go back in the 60s and look at what Drake calculated, or Carl Sagan and other people, or Al Cameron, they found civilizations by the millions. This was the prevailing idea. There was a lot of optimism in those days. There will be many around us. If you look at more recent evaluations, the numbers go down. But they can well go down to 1. There is nothing against that. I mean, we are here, that's all we know. Does this mean that this equation is totally useless? I don't think so. It played a very important role during all that time in shaping our thoughts about this very complex thing, extraterrestrial life and intelligence. And in fact, it shaped the program of research, even indirectly, because what we do now in those, we don't look around any kind of stars. There are many stars in the galaxy. We said that the small stars are more numerous, fine, but the massive stars are much more brighter and easy to see. But we don't look around them, we don't care, because we know they live just for a few million years. And in a few million years, our experience tells us that it's hard to develop life around them. So we just discard them. So the programs, the surveys of stars, of useful stars, focus around solar-type stars, not even around Proxima Centauri-type stars, because they are so less bright than the sun that we think that if they have habitable planets, they have to be very close to them and affected by tidally locked to them. Tidally locked means that they present always the same face to their star, as the moon to the earth, as Mercury to the sun. And these are also not interesting for life in the first place, because they will be very much irradiated from one side and very cold from the other side. So we need to find around solar-type stars and in the habitable zone. So all this kind of the agenda was established by the Drake equation. But of course the next steps are far away from our research now. So what is the meaning of this? You can ask, what is the meaning of this equation, in fact? It's perhaps easier to understand it. I'm sure you have all done physics. You know the equation of radioactive decay. This is the number of nuclei now, dn over dt, that decay in per unit time. It's proportional to the number of the nuclei at a given time divided by the half-life of the nuclei. This is the equation of radioactive decay. Now, if you are in a steady state, if the number of nuclei that disappear is the same as the number of nuclei that appear, the production term is equal to the destruction term. Okay, this is the destruction term. Then you can calculate from this, the production term is also the destruction term, n over t, and you can solve for the n, the number of nuclei that have at any time. Is the production rate times the lifetime of the nucleus. This is from radioactivity, nothing to do with the Drake equation. But you see that the Drake equation has exactly that form. There is a number of civilizations, there is a lifetime here, so this, and all these terms there, their product is the production term. This is the creation rate of such civilizations. It's exactly that term. It means in a steady state. This is why it is important to have also to include the lifetime there. Otherwise, it is difficult to understand what the Drake equation means. And he was lucky in a sense, because you can apply this equation to our galaxy. We know that spiral galaxies like the Milky Way evolve slowly, more or less at the same pace. It's not like ellipticals that Mark mentioned in the beginning. Elliptical galaxies are very red because they formed almost all their stars many billions of years ago, nothing after that. So if we were living in an elliptical galaxy, the Drake equation would not apply. But for a spiral galaxy like the Milky Way, it applies. the steady state, the Milky Way is more or less in a steady state, so it is reasonable to apply this equation. But Drake didn't know that in that time. We knew very little about galaxy evolution at the time of Drake. Okay, so now we shall play a few games with this Drake equation. As I said before, it has no predictive power. Still, we can constrain it somehow. Instead of putting other terms there or doing, we shall group the terms in three. We shall leave the lifetime as it is. We shall take these three first terms under the name of an astronomical term, and the other three a biotechnological term. Why? Because this one we now start having an idea of how the values that you can put there through the observations, not through theory. This one we know nothing, and this one we know nothing about. But at least we can put them in a two-dimensional diagram. Okay, so the first one, the astronomical factor. The second one, we shall call it biotechnological factor. The last one, the lifetime in the corresponding technological phase. We know from the astronomical factor, we know what is the star formation rate in the Milky Way. We have various ways to evaluate it. I will not insist in one of them. I will go just to the result. We think that there are about 10 stars per year today formed in the Milky Way. And if we need just solar type stars, because are the most appropriate, they are long-lived, they allow for the right, for planets to be in the habitable zone, not tidally locked, so they are 10% of the total. So a nice round number, if you want to keep just one number, you have to know that every year in our galaxy there is one star like the Sun formed. Okay?
What's the slope here?
Sorry, the slope?
What's the slope here?
The slope of what?
No, the line.
Of the line here, of the IMF, is between 2.3 and 2.5, 2.6, the IMF of group. Yeah, it goes very rapidly down for the massive stars. Okay, now what fraction of them may have Earth-like planets in the habitable zone? This is the result now of the observations made in the last 10 years or so, mostly by the Kepler telescope of NASA. You see there, as a function of the size expressed in Earth radii, how many planets have been discovered, and they are corrected by a factor which accounts for the bias there are, because they are less easy to detect when they are closer to their star. They have here, so this is, they add this thing to complete for that, okay? So this is the number of planets, small planets, these are the ones we are interested in. And this is the orbital period, how many planets were detected as a function of the orbital period in days. You see that we detect planets that are orbiting their stars in less than 100 days. Less than 100 days means they are very close to their star, closer than Venus is to the Sun. So these are not in the habitable zone, in fact. So what these guys did, there is a paper by Betigura et al., they took the cumulative fraction of Earth-sized planets as a function of the orbital period. So this is cumulative fraction, where we start with 0 and you add up everything. And you see that they have data up to here, about 100 or 200 days. Here it's 100 days. But we are interested, the habitable zone in our solar system is outside that. The Earth is 365 days. So what they do is to extrapolate. They take this and they extrapolate. Okay, between 200 and 400 days. Because we consider that the habitable zone is in that region. And then with that they find that the number here is, they count what should be the numbers here, is 6%. Okay, so we shall say optimistically that about 10% of the stars, solar-like stars in the Milky Way, may have planets in their habitable zone. Okay, this is the thing that changed since the time of Drake through the recent observations. So we can say something for the first terms, the first term, this one, the astronomical term, we can put it on 10% per year, or for 0.1 per year. Okay, but then there remain the two other terms. So what we will do is the following. We shall plot the two terms. Once we know the first one, 0.1 per year, we shall fix it. And we shall plot the two others, of which we know nothing, in a two-dimensional diagram, a logarithmic diagram. It is not true that we don't know anything about this one. This is the product of three probabilities, each one is less than 1. So the maximum value of the product is equal to 1. We know its maximum value. It's bounded by 1 from above. We don't know anything about below. And for the lifetimes, we know nothing, of course. We can lay anything. Now, in a diagram like this, n, the product of two things, in a log-log diagram, n equal constant is given by straight lines. Okay, this is n equal 1, 100, 10,000, 10 to the 6. And of course, all this part, below, this part here, is less than 1. So for all this combination of the factors, we are alone, civilization is alone in the galaxy. So it's this part of the diagram that becomes interesting. So what can we say about that? We have to take into account now the dimensions of the galaxy. The galaxy is basically a cylinder. We know its dimensions, we know its the thickness, about 2,000 light years. And we shall assume that it is filled with civilizations, more or less of at equal distances, n spheres of radius r. It's fairly easy to calculate the average distance of those spheres if they fill the galaxy. These are the formula. It depends on the number of how many spheres you have. But the number is what we have seen here. You can pick, depending on the combination you have, you can pick any one of those numbers. But once you fix this number, then you can calculate the average distance between the civilizations. If you have few civilizations, the distance is huge. It's down here, if you have just a few civilizations, it's 10 to the 5 light years. If you have many civilizations, billions, even if you have 1 billion civilizations, the closer one is at a distance of 30 light years. Okay, distance in the galaxy is very high. If you have 1 million civilizations, the average distance is several hundred light years here. So this is one thing, just geometry, nothing more than that. And then you can also ask yourself, what is the lifetime of such civilization? Because n is the product of this factor that we have fixed and two other factors. If we give to this factor the maximum value, which is equal to 1, then there is a minimum value for L in order to have a given number of n. If we want to have at least one civilization, if we want to have many civilizations, 10 to the 5 civilizations here, and if this is equal to 1, this is 0.1, then this has to be at least 10 to the 6 in years, 10 to the 7 up there. So there is a minimum value of life for every value of n here. If you fix this to its maximum, we give life the maximum of chances to appear, equal to 1. Then you have L, the lifetime has to be of at least some value. And the next step is to consider communication. If you want to have two-way contact between close neighborhoods, then the minimum lifetime required is twice the time required by light or radio signals going at the light velocity to go through that distance. The distance that we have just seen here depends on the number of civilizations. So there are some implicit relations. D is a function of the number of civilizations and the dimensions of the galaxy. And the number of civilizations is a function of those two factors. And the minimum lifetime is also here is a function of those things. How can we plot all that in this diagram? In that diagram, you see what is the minimum. This part of the diagram is where the lifetime is sufficient to allow for two-way communications. And you see that there is a minimum, even for the maximum lifetime of the factor F biotech, there is a minimum of lifetime necessary of a few thousand, 10 to the 3 years, a few 10 to the 3 years there. So only civilizations living quite long, more than a few thousand years in the technological phase, allowing to exchange radio signals, could be able to have communication, two-way communication. All others in this part of the diagram, they do not live long enough to exchange radio signals. And then this part of the diagram is also useless because any civilization is found alone in the galaxy during its lifetime. So you see the importance of this factor here, the lifetime, for this kind of enterprise, which is not obvious in the beginning. We are spending a lot of time trying to imagine conditions for the appearance of intelligent life forms. How much, what would be the fraction that would allow for development of life, intelligence, or complex life. But there is a factor which is even more important, which is the lifetime in this form. And why is it more important? Because of the very large range that it can have, what we call a dynamical range in a variable. It can go from several thousand years, which is even above us. We are around here now. Our civilization is in the technological phase of radio communicating for about 100 years, only for the last century. But it can go up to billions of years. So this factor is also very important and has to be taken into account. So the last part of my talk would be about something else that has also contributed a lot to discussions on extraterrestrial intelligence, and the so-called Fermi paradox. I guess everybody knows who was Enrico Fermi, one of the greatest physicists of the 20th century. He got the Nobel Prize in 1938 for his theory of beta decay. He was most probably the last great physicist who was equally good in theory and experiments. You know, there is a lot of specialization these days. People, other theoreticians or experimentalists. He was the last great physicist who was good at both of those things. And in a lunchtime discussion in Los Alamos laboratory, where he was working, he has also participated in the Manhattan Project, which was, as you know, the construction of the American atom bomb in the 40s. And it was made in Los Alamos laboratory. And he discussed with Edward Teller, another famous physicist, and their colleagues on the UFOs, unidentified flying objects, which, as you probably know, the first reports on UFOs were made in 1947 in the United States, and was quite some excitement about them. So they very rapidly concluded that UFOs were not of extraterrestrial origin. But then Fermi, according to what his colleagues were saying many years after, he made a back-of-the-envelope calculation. He was famous about doing simple calculations of order of magnitude. And then he asked his famous question to his colleagues, where are they? And by that he meant that we have no sign of extraterrestrials on Earth, either extraterrestrial beings, ships, artifacts, robots, whatever. So if there are many of them in the Milky Way, where are they? Why some of them have not visited us up to now, or have not left any trace of their presence? And then this discussion was forgotten for a long time. The first time I have found this phrase is on it appeared as a footnote in a paper by Carl Sagan in Planetary and Space Science in '63. Just a footnote. And then in the book, if there is one book you should read on extraterrestrial intelligence, this is the book written by Sagan and Shklovsky in '65. It's a long time ago. We knew nothing about extrasolar planets and so on. Still, it's the most intelligent book and the most comprehensive that you can ever find about our thoughts on extraterrestrial intelligence. And then again, this phrase appears there, somewhere, with no comment. Obviously, Sagan learned about that discussion. He understood that it may mean something for the quest for extraterrestrial intelligence, but he could not make his mind on how to deal with that. And then, quite independently, as it happens often in physics, an American astronomer, Michael Hart, rediscovered the argument of Fermi and discussed it in a paper in Quarterly Journal of the Royal Astronomical Society in '75. And his conclusions were that there are few other civilizations and probably none in the Milky Way. And so the research of extraterrestrial signals is a waste of time and money. Remember, this happened in a period where the research of extraterrestrial signals was very active. There were projects, several projects on even Russian projects in Australia to search for extraterrestrial signals. And the final point was that our descendants will colonize the galaxy since the others are not interested. And this paper started a big debate because it went against people like Sagan or Drake who wanted to look actively about extraterrestrial signals. And it is only after that that Carl Sagan gave the name the Fermi paradox to the fact of the absence of extraterrestrials on Earth. In 1975, so 25 years after Fermi had formulated his question. A quarter of a century after that, for the first time, the term the Fermi paradox appeared in the literature. Now, as it happens quite often, Fermi was not the first one to find that. And Hart also discovered it independently. He didn't know about Fermi's discussion. But other people before have thought about such things. This happens quite often in the history of sciences. And the oldest example we have is from the French Bernard Lebouvier de Fontenelle, who was the secretary of the Academy of Scientists, and he wrote probably one of the most popular books on the, it was in French of course, but this is the English edition, Conversations on the Plurality of the Worlds, who is presented in the form of a dialogue between a nice a young Marchioness and the philosopher. He is supposed to be not very knowledgeable about various things, but quite intelligent to ask interesting questions. And at some point the philosopher says that intelligent beings exist in other worlds, such as the moon. But to that, the Marchioness replies, this is nonsense. If this were the case, the moon's inhabitants would already have come to Earth. And the only thing that the philosopher finds to answer, remember these are the ideas of Fontenelle. He's trying to put them through a dialogue, which makes the discussion more vivid. So the time needed to master space travel is probably too long. If it is greater than 6,000 years, we can understand why they have not yet been here to visit us. Why 6,000 years? Because at that time, the age of the Earth, we had no idea, like Francis knows now, the age of the Earth. People were based on biblical accounts. And biblical accounts, by counting the generations from Adam to Moise to all the other people mentioned in the Bible, if you put them everything together, makes an age of 6,000 years. So, but remember, please notice that in the example of Fontenelle, the situation is completely symmetric with respect to the extraterrestrials and the Earth people. We didn't have come to go there, they didn't have come to come here. Because both us and them have the same time in our disposal, 6,000 years. In the case of Fermi, the paradox is based exactly on the fact the situation is not symmetrical. We cannot go to the stars now, but probably we shall be able to do it in a few hundreds or thousands of years. But if they exist, we know that half of the stars in the Milky Way appeared before the Sun. So they had all the time, billions of years to come here, or millions of years. So in the Fermi's case, the situation is not symmetrical. Here it is symmetrical. And then independently, the father of astronautics, the Russian Konstantin Tsiolkovsky, also around 1912, wrote, we have been, he believed, Tsiolkovsky was a mystic. He was the one who made all the theoretical framework of astronautics, the famous rocket equation, how rockets can be propelled in the void. And, but he was also a philosopher and believed a lot on the future of mankind in the universe. His famous phrase was that the Earth is when humanity appeared, the crow, Okay, there is a word that it doesn't come to mind. But nobody stays all his time, spends all his time where he was born. So at some point he thought about the exploration of space and the expansion of mankind in the universe, and he realized that if this was the future of man, then this would be also the future of other civilizations in the galaxy. And in order to explain why they have not come here, he said, we have been set aside as a reserve of intelligence in order to allow our species to evolve to perfection and thereby bring something unique to the cosmic community. So you see, these were ideas already not only about the Fermi paradox, but how to solve the Fermi paradox. Today it can be formulated as following. Our civilization is not the only technological civilization in the galaxy. Now, this is based, it's an advanced form of the so-called Copernican principle. Remember what Mark has said before about our concept, about models of the universe, representations we had. In the beginning, we thought that the Earth was something special in the center of the universe, and so was our solar system. Then we learned that we have nothing special, not only in space. We are somewhere in the galaxy, not in the center of the galaxy. Our galaxy is somewhere in the universe, but also on time. We are not born in the beginning of the time. The sun has 4 billion years of age. And so in the same, if you extend this Copernican principle, it is natural to think that we are not alone also in the galaxy. It's a kind of pre-Copernican reasonment. Okay, so this is the one assumption of the Fermi paradox here. It's purely Copernican. We have nothing special, we are not alone. And then we are typical in every point. In particular, we are not the most advanced, not the only one desiring to explore the universe and communicate with others. Now, this is the only technical thing here. Interstellar travel is not very difficult for a civilization more advanced than ours. And some civilizations must surely have undertaken such travels. And then the final assumption is that the colonization of the galaxy is relatively rapid. If you look at, okay, it would take a lot of time to discuss schemes that have been proposed for that, but the time scale in all cases is an order of several tens of millions of years. So this is a small fraction, 1/100th of the age of the galaxy. If you put all those things together, then the conclusion is that they should be here. And the fact they are not here constitutes the Fermi paradox. As you are aware, I'm sure, about paradoxes, paradoxes are based on assumptions that one or more of them are not correct. Okay, this is the solution to a paradox. And this means that one or more of those assumptions are not correct. But which one? Depending on whom you are discussing, you find the solution. I mean, for instance, you can say to yourself that this never happens. I mean, no one would be able to propagate into the galaxy, or interstellar travel is not possible. It's impossible. But there is no a physical limit to interstellar travel beyond light velocity, light speed, which cannot be exceeded. But even that is not sufficient to explain the Fermi paradox. Or a lot of sociological explanations are based on that, to argue that our civilization is not typical. So again, a form of pre-Copernican. And the final explanation for people that are against the idea of extraterrestrial intelligence is this one. This assumption is wrong. Okay, so there are many other solutions to the Fermi paradox. There was a book by Stephen Webb in 2002, 50 solutions to the Fermi paradox. Now he made, in 2013, a new edition, 100 solutions to the Fermi paradox. There are a lot of people proposing solutions to explain why we are here. So there are basically three big classes of solutions. The first one is that they are here, in fact. There are people who believe that they or their probes came in the remote past and they observed or even created or assisted the creation of our ancestors. And they probably left their probes on Earth and somewhere in the solar system. And people in this class are like Arthur Clarke, the famous science fiction author, at the origin of 2001, the best science fiction movie of all time. Remember the history of the monolith and the extraterrestrials that came on Earth 4 million years ago with an infused intelligence in the apes. Michael Papagiannis was a Greek astronomer in Boston, and he was the founder of the, not the division, the committee number 51 on bioastronomy. He was also of that opinion. He thought that extraterrestrials have left their presence on the asteroid belt. He wrote a couple of papers on that. Okay, so there is one possibility that they have come here and they left traces somewhere. The huge amount of the solution is that they are there, but there is a but. They exist, but they do not wish to come. They have other interests. They are not able to come because they are rapidly destroyed. This was what Fermi thought. Remember, in the 50s, even in the early 60s, the fear of a nuclear holocaust was very much felt in the West, because there was the terror equilibrium between the United States and the Soviet Union. And a lot of people felt that as a big threat, that civilization will be rapidly destroyed by nuclear weapons. Or because, like Fred Hoyle and Frank Drake think, interstellar travel is impossible. Alternatively, they did come and they are just observing us without interfering, or they have put us in a cosmic quarantine. This is what Tsiolkovsky thought, or John Ball, another American astronomer. And this is also, for those of you that are fans of science fiction, on the Star Trek, this is the famous Prime Directive. Okay. When the crew of the Star Trek discovers primitive civilizations, they do not have right to interfere with them, to speed up their development. So this is more or less this idea there. And then the final solution is that they are nowhere and we are alone. And this was the idea by Hart, by Frank Tipler, by other astronomers, but most importantly by biologists. Ernst Mayr is a Nobel Prize in medicine. George Gaylord Simpson is an important biologist, and others, because biologists are less enthusiastic than astronomers about the possibility of another form of intelligent, complex life in the galaxy. They find that the evolutionary path that led to the emergence of intelligence on Earth is quite improbable. There have been 5 major catastrophes in the last 530 million years of multicellular life on Earth. Just to pick up the last one, 65 million years ago, a big meteorite hit the Earth, destroying dinosaurs. If dinosaurs have not been destroyed, dinosaurs have reigned for 200 million years, almost, 150 million years on Earth. If it were not for that meteorite, we would not be here now, because mammals evolved after the disappearance of dinosaurs, to their complexity and intelligence. So from that perspective, it appears that the evolution to some intelligent life forms is quite rare, and perhaps we are here by pure chance. Now, can we, and this will be my last, one of my last few graphs, we can connect the Drake equation and the analysis we did to the Fermi paradox. And this is the first time that somebody has done that. Instead of, remember, we found a room in the diagram of the biological factor versus the life, where the minimum lifetime of civilizations has to be twice the distance divided by the speed of light or exchange of radio signals. We can apply the same reasoning now, but instead of the speed of light, because we know that interstellar travel cannot be based on the speed of light, a fraction of the speed of light. Then we have to make assumptions about how rapidly civilizations can disseminate in the Milky Way. And we get a similar diagram, except that now the region is bounded from the left by what we assume from for the expansion, the velocity of expansion divided to the light speed. So if it is 10 to the minus 2, 100th of light speed, that this part of the diagram is where the Fermi paradox still holds. If civilizations live long enough, if their probability of appearance is quite high, then in this part of the diagram
we can ask ourselves, where are they? In contrast, if civilizations live less than a few 100,000 of years, and we are in this part of the diagram, and then when we can understand why they are not here. And of course, in all this part, again, each civilization arrives, lives for a few thousand years, dies, but being alone in the galaxy. And but you see that in this is a log-log diagram, okay? And in this diagram, the condition for exchange of radio signals, this was here, okay? It's not far away from the conditions for interstellar travel, contact through interstellar travel.
So one could ask the following thing. Suppose that they exist and they desire to find other civilizations and to communicate with them, and they live long enough. What strategy would they adopt? Would just search radio signals if they live for 100,000 years? Because you can look for radio signals and detect nothing. Other civilizations may not be emitting radio signals during that time. So wouldn't it be safer to plan for an interstellar research project, going and see there what happens? And this is also true, for instance, with the current projects about extrasolar planets. You know that the next step now, we hope that in a few years from now we shall be able to detect various tracers indicating life activity on the surfaces of planets. But suppose we found ozone, for instance. What can we do with that? How should we know if there is life in what form? Bacteria? I'm not sure that a lot of people would be interested in that, if there are bacteria in another planet. Could they be apes? That would become more interesting. But apes do not radio communicate. We have no way. The only way to be able to say something is to send an interstellar probe and look there. And this is what we could have done. So if we can think of such things, the others would also have thought about that thing. So it appears more interesting for them to undertake a program on interstellar travel and exploration. In that way, they would have a definite answer within their lifetime, if they live long enough. So, to come to the next, to this last diagram, the quest for extraterrestrial intelligence is not far away from the point for intelligence, not for life, intelligence, from the point of the ancient Greek philosophers. In fact, those guys have said about everything, I mean, we could say. They have thought about everything. So Epicurus, 3 centuries before Christ, has said to consider the Earth as the only populated world in infinite space is as absurd as to assert that in an entire field sown with millet, only 1 grain will grow. This is more or less the argument today. Of course, we do not speak about the infinite space. It has been replaced by our galaxy, which has 100 billion stars. And for many people, 100 billion is a large number. Quite large, and then we have the probability to find a lot of other people like us there. But we have this paradox on the other hand. Where are they? Why they are not here? And we are between, none of those 2 arguments is decisive, because they are based, both of them are based on what we know here on Earth. You cannot make statistics with one life form, intelligent life form on Earth. So we are now at a point we can put those questions in a more scientific ground, and using modern science and telescopes and computers to have a beginning of answer to those questions. But, and as correctly Cocconi and Morrison put it, the probability of success is difficult to estimate, but if we never search, the chance of success is 0. And I will leave you with the last view graph, which is this one. Sometimes, this is a humoristic, sometimes I think that the surest sign that intelligent life exists elsewhere in the universe is that none of it has tried to contact us. They are clever enough not to want to have anything to do with us. We are because we are very crazy. And okay, so thank you very much.